Welcome to our lecture on complex analysis. Today we are going to explore one of the most powerful and elegant concepts in mathematics, residues at poles. If you have ever wondered how engineers and physicists solve seemingly impossible integrals with just a few lines of algebra, you are in the right place. Let us dive in and demystify this incredible mathematical tool. Let us start by building some intuition. Imagine a flat trampoline, which represents our mathematical space, the complex plane. Now, if you place a heavy bowling ball on it, the fabric stretches down infinitely deep at that exact spot. In complex analysis, that deep, infinite pit is called a pole. It is a specific point where a mathematical function blows up to infinity. Now, imagine walking in a circle around the edge of that pit. The residue is a special number that tells us exactly how much the function is twisting or accumulating around that specific hole. Think of it like a clogged drain in a sink. The residue measures the strength of the whirlpool spinning around it. Now that we have our trampoline analogy, let us look at what this actually looks like mathematically. Here you see a three-dimensional surface representing a complex plane with the real and imaginary axes clearly labeled. Right in the center, at the point Z0, the surface plunges downward into an infinite pit. This is our pole. Notice the circular arrow looping around the rim of this pit? This loop represents the path we take around the singularity. The label shows where the residue is extracted. By evaluating the function along this circular path, we capture that single highly valuable number, the residue, which completely defines the behavior of the function around this infinite drop. Moving from our visual analogy to formal mathematics, we first define an isolated singularity. This is a point where a function is undefined or broken, but works perfectly fine everywhere immediately around it. A pole is a specific type of isolated singularity where the function shoots off to infinity, much like how 1 over z behaves when z is 0. When we encounter a pole, we can express the function using a Laurent series, which is an infinite sum of terms that includes fractions. If you break the function apart into this long sum, the residue is specifically the coefficient attached to the term with exactly 1 power of z minus z0 in the denominator. It is the top number of that specific fraction. This formula we just saw leads us to an important question. How do we actually calculate that residue without writing out an infinite series? The answer is this highly useful limit formula. Conceptually, to isolate the residue, we multiply the entire function by the factor z minus z0. This cancels out the problematic denominator. Then, we force z to get closer and closer to z0 by taking the limit. When we do this, all the other terms in the series vanish to 0, leaving only our residue r. In this formula, r is the residue we are solving for, and the z minus z0 term is the exact factor causing the blow-up. If the pole location z0 changes, we simply adjust the limit and the multiplying factor accordingly. This is a massive shortcut for our calculations. Before we move on, let us see this with a concrete example. We are asked to find the residue of the function f of z equals 5z divided by z minus 2, specifically at the point z equals 2. First, we look at the denominator. When z is exactly 2, the denominator becomes 0, which means the function blows up. Because the z minus 2 term is not squared or cubed, we know this is a simple pole. Therefore, we choose our simple pole limit formula. We start by setting up the limit as z approaches 2, and we multiply our function by the factor z minus 2. This is the crucial step where we plug the drain, so to speak, so we can measure what is happening around it. Continuing with our calculation, notice how the z minus 2 on the top and the z minus 2 on the bottom perfectly cancel each other out. This algebraic step removes the singularity entirely, leaving us with a very simple, well-behaved expression, the limit of 5z as z approaches 2. Now that the dangerous part of the fraction is gone, we can safely evaluate the limit by substituting the number 2 in place of the variable z. 5 times 2 gives us 10. This means the residue of this function at the pole z equals 2 is exactly 10. Physically, if this were an electrical circuit, this number would represent the exact amplitude of the vibration at that resonant frequency. Now that we have mastered simple poles, we must ask what happens if the pole is stronger. Sometimes the factor in the denominator causing the blow-up is squared, cubed, or raised to an even higher power. When this happens, we call it a pole of order m. The symbol m simply represents this order, which is the highest power of the denominator causing the singularity. Because the singularity is more severe, simply multiplying by the factor once will not clear the denominator completely. We need a more robust mathematical tool to isolate the residue, which means we will have to introduce derivatives into our process to strip away the extra layers of the pole. Here is the formula we use for these higher order poles. Conceptually, it does the same thing as before. It clears the denominator and isolates the residue. First, we multiply the function by z minus z0 raised to the power of m to completely clear the denominator. But because there are multiple powers, we must take the derivative exactly m minus 1 times to isolate the residue. Finally, we divide by the factorial of m minus 1 to cancel out the constant numbers that drop down during differentiation. In this formula, m is the order of the pole. If m increases, say from 2 to 3, we have to take more derivatives and divide by a larger factorial. It looks intimidating, but it is just a systematic way to peel back the layers of a stronger singularity. Let us apply this new formula to a slightly harder problem. We are given the function f of z equals z squared divided by z minus 1 squared, and we need to find the residue at the point z equals 1. First, we identify the pole. The denominator becomes 0 when z is 1. However, notice that the entire denominator is squared. This means we are dealing with a pole of order m equals 2. Because m is greater than 1, we must use our higher order pole formula. We start by plugging in m equals 2 and z0 equals 1. Our first mathematical step is to multiply the function by z minus 1 squared, which is designed to perfectly clear out that problematic denominator. Continuing with our setup, we plug everything into the formula. We need to take the derivative m minus 1 times. Since m is 2, 2 minus 1 is 1, so we only need to take the first derivative. We also divide by 2 minus 1 factorial, which is just 1 factorial, or simply 1. Now, look at the terms inside the brackets. The z minus 1 squared on the top and the bottom cancel out beautifully. This leaves us with just z squared inside the derivative brackets. The factorial fraction in the front simplifies to 1, so it effectively disappears from our calculation. We have successfully removed the singularity and simplified the expression. Now for the final steps. Our only job left is to take the first derivative of z squared with respect to z. Using basic calculus power rules, the derivative of z squared is simply 2z. We have now successfully completed the differentiation step, and we are ready to apply the limit as z approaches 1. We substitute the number 1 into our simplified expression 2z. 2 times 1 gives us a final result of 2. Therefore, the residue of this function at the pole z equals 1 is exactly 2. Even though the pole was more complex, this step-by-step process safely guided us to the single number that defines its behavior. Physically, this tells us the exact strength of the system's response at the specific resonant frequency. You might be wondering, why does all of this matter in the real world? The truth is, residues are the ultimate mathematical cheat code. In engineering and physics, we constantly need to calculate complex integrals to understand how systems behave. For example, in electrical engineering, when designing a filter for a radio, the poles represent the resonant frequencies where the circuit vibrates the most. The residues tell the engineer the exact amplitude or strength of those vibrations. Without residues, calculating these values would require impossible amounts of computation. By simply finding where the denominator is zero and calculating the residue, engineers can predict the stability of airplanes, the flow of heat, and even the behavior of quantum particles. Let us wrap up with the key takeaways from today's lecture. First, remember that a pole is a specific point where a mathematical function blows up to infinity, like a deep pit in the complex plane. Second, the residue is a single highly valuable number that captures exactly how the function behaves around that infinite pit. Third, we can easily extract this number by multiplying the function to cancel out the singularity and then taking a limit, using derivatives if the pole is of a higher order. You have now covered the full foundation of this topic. Mastering residues unlocks the ability to solve incredibly difficult integrals with just simple algebra and basic derivatives. Great job today, and keep practicing.